in beam, the transverse shear loading would be from the roof or ceiling. From the ceiling, the transverse load would be there like this. So this is, if this is the beam, this is the beam, this is the cross section of the beam, okay? This is the cross section of the beam, and on this cross section, this is the neutral axis. This is the neutral axis. Above the neutral axis there are some fibers, below the neutral axis there are some fibers. So we need to see on those fibers the distribution of bending stress as well as shear stresses, okay? So this is the neutral axis. So above the neutral axis and below the neutral axis, the distribution of bending stress would be linear, as we have already seen from the distribution how sigma b are going to vary accordingly y. They are going to vary linearly, okay? So now I am going to draw this. So let's assume that transverse shear loading is from upward to downward. So the loading is downward on the cross section. So if the loading is downward, then this beam is, if I will tilt it like this, then this beam loading is downward, then it is going to bend like this. So the upper fiber of the beam, I mean if I say the upper fiber from the neutral axis, the upper fibers will be in compression, and the lower fiber of this particular beam, which are below the neutral axis, they are going to be in tension. So upper fiber, neutral axis, upper fiber, they will all be in compression, and the fibers which are below the neutral axis, they are going to be in tension, okay? So like this, upper fiber, they will be in compression, and the fibers which are below the neutral axis, they will be in tension like this. So this is the cross section, this is the neutral axis, and all the upper fibers from the neutral axis, they are going to be in compression. So this is the stress which is trying to compress this particular cross section which are above the neutral axis, and these are the component of stresses which are trying to elongate it. So these are the tensile stresses, okay? So this is the bending stress distribution. Now let me draw the shear stress distribution on the particular cross section. Let's see, this is the cross section. As we have already seen that tau is a function of y square here. So we already know that shear stresses are going to vary parabolically, okay, from a particular fiber to fiber, okay? So how would be the distribution of this shear stress? It would be something like this, parabolically, with maximum value at the neutral axis, like this. This is the maximum value, tau max, okay? So this is going to be the maximum value at neutral axis only. So the variation is something like this. This is the shear stress distribution on the particular cross section in a beam, and loading is the same, that is transverse shear load is on the beam, okay? So this is the shear stress distribution on the particular cross section on the beam, okay? As we have already seen, this is varying parabolically. Now the significant points, the remarkable points which I need to discuss from here, from these two curves, there are some conclusions which we need to draw from here. What are those conclusions? Let me be very specific with that. So there are some conclusions which we need to draw from here. First one, the first conclusions. First one is that if we see the upper fiber and top fiber and bottom fiber, let me write the values. This is the sigma b max value, sigma b max for tension, and this is the sigma b max for compression, okay? So if we consider the top fiber and bottom fiber of the cross section, we can clearly see that sigma b values are going to be the maximum on either side, or either on the top or on the bottom fiber. The sigma b values are maximum. Here in the case, if we talk about this symmetric section, or like here we have a rectangular cross section. In all the rectangular cross section or symmetric cross sections, sigma b max compression as well as sigma b max tension values are going to be the same. But if this cross section is not symmetric, like if we have any T section or W section, then this sigma b values, compression and tension maximum values, those would not be the same. But this is the clarity. Certainly we can say that sigma b will be there on the top fiber as well as on bottom fiber. They are not going to be zero. We can clearly say that sigma b will have some value either in tension or in compression. Maybe it may be maximum or minimum, but it must be having some value. It would not become zero. But if we talk about the shear stress on the top fiber as well as on the bottom fiber, as we can clearly see from this figure or from this distribution, that sigma this curve is being closed from the on